So in this video, we're going to look at the extreme value theorem applied to a case where we have a radical function. And what's going to make this case interesting to look at is that we have a cusp in the graph of the function. So we have a place where the derivative doesn't exist. So just like in previous videos, we want to find the global extrema for this function. We are looking for that. That means we are looking for the highest output value and the lowest function output value of the function, and we're going to use the extreme value theorem, which means that we're working over a closed interval. That's the key with the extreme value theorem, is we're defining a function over a closed interval, and as long as we have that closed interval, the extreme value theorem says there's going to be a largest output and a smallest output on that closed interval. So we're going to step through the same four-step process that we've been using. First, we need to find the critical numbers for our function. So our function is the function f of x equals 2x minus 3x to the 2/3. And then our critical numbers are going to occur either where the tangent lines are horizontal or where the derivative is undefined at the cusp. So we know we need to take the derivative of the function as our next step, because to find the critical numbers of the function, the places where the derivative is undefined or equal to 0, we need to find the derivative. So the derivative of 2x is just 2 minus 3 times the derivative of x to the 2/3. Well, that exponent 2/3 is going to come down, and then the 3's are going to give us a 1. So it's going to simplify to 2 times x, and then we're subtracting 1 from 2/3, which is going to give us a negative 1/3. And this is a case where we really do need to clean things up a little bit on the derivative. So I want to recognize that the derivative is the same as 2 minus 2 over x to the positive 1/3. And then finding a common denominator, I would multiply this by x to the positive 1/3 over x to the positive 1/3, and that's going to give me a derivative cleaned up that looks like 2x to the 1/3 minus 2 all over x to the 1/3. And I want to recognize that the common factor of 2 is showing up in the numerator, so I could also write this as x to the 1/3 minus 1 all over x to the 1/3 with the constant 2 factored out. So once I have the derivative, now I'm in a position to do step 1, which is find the critical numbers. And the critical numbers either occur when the derivative is equal to 0. That's where I get the horizontal tangent line at this relative minimum right here. And the only way for this derivative, because it is a ratio of two expressions, the only way for the derivative to equal 0 is for the numerator to equal 0. So first I set the numerator equal to 0. I solve and then solve for x. So I get x to the 1/3 equals 1. So I need to cube both sides. 1/3 times 3 is 1. X to the first is x, so I get x equals 1 as a critical number. And then the cusp is going to happen when the derivative is undefined. So now I need to take the denominator and say, when will that denominator equal 0? That's when the derivative won't exist. That is the x value at which this cusp will happen. So I say, hey, here's one critical number, and then I say, when does x to the 1/3, the denominator of my derivative, equal 0? And again, I would be cubing both sides, which would give me x is just equal to 0. There's my second critical number. So once I find those critical numbers, I move on to step 2 of the process, evaluate the function at the critical numbers. So we need to evaluate f of 0. So we put 0 into the original function, so it's just going to be 2 times 0 minus 3 times 0 to the 2/3, which is just going to be 0. So the first output I'm interested in is f of 0 equals 0. My second output I'm interested in is f of 1, which is going to equal 2 times 1 minus 3 times 1 to the 2/3, which is just going to be 2 minus 3 is negative 1. So the second output I'm interested in is the output of 1, sorry, the output of -1 that happens when I input +1 to the function. So that finishes step 2, which is to find the function outputs at the critical numbers of the function. And then the extreme value theorem tells us that either the output's going to be at the critical numbers or at the closed interval endpoints. So I also need to evaluate f of x at -1 and 3. So I'm going to work on that next. So f of -1 equals plug -1 into the original function. So -3 times -1 to the 2/3. So here I get a -2 minus, and I want to recognize that this is going to be -1. There's a 2 in the numerator, so it's -1 squared, and then we're taking the 1/3 root of that. So we're going to get -2. -1 squared is 1, and the third root of 1 is 1. So we just get -2 minus 3 equaling -5, and that's matching up with what the graphical evidence is telling us. So I get f of -1 generates an output of -5, and then I need to do the endpoint 3, and this one's not going to come out nicely. So when I evaluate f of 3, I'm not going to get an integer or rational number output. I'm going to get an irrational number. So I do 2 times 3, plugging the 3 into the original function, minus 3 times 3 to the 2/3 equals, let's see, I have a 3 showing up on each spot, so I can factor a 3 out, and that will give me 2 minus 3 squared is 9. So I'm taking the third root of 9. So the number that when I multiply it by itself 3 times gives me a 9, and that's going to be an irrational number. It's not going to come out nicely. So when I plug in 3, I get 3 times 2 minus 9 to the 1/3 power. So one thing you can do with it is approximate it so you can make an easy comparison with the other numbers. And so here GeoGebra has approximated it for me. When I input 3, the output is about, so approximately equal to -0.24. And then the final step of the process then, step 4, which isn't in the box, is to evaluate those function outputs. We're looking for the extrema, the largest and smallest outputs on the closed interval. So it's just a matter of evaluating the function outputs and saying which one is biggest and which one is smallest. Those are our extrema. So I see that I have a global maximum. I have a largest maximum. I have a largest output of 0. Right? 0 is the biggest of the 4 output numbers. A global maximum of 0 on the closed interval from -1 to 3. So a global maximum of 0 at input 0, output 0. So the maximum occurred at the cusp, which is why it was important to determine when the derivative was undefined. And that's probably the easiest thing to forget to do, which is why drawing the graph first and seeing that you're expecting a cusp is useful. So global maximum and a global minimum of -5 was the smallest output on the closed interval from -1 to 3 of -5 at, and that occurred when we input -1. We got an output of -5. So there's our extrema, our global max and global min values on the closed interval.